So a new idea. We're going to talk about how to find center of mass and moments of inertia and radius of gyration about an axis for these really thin plates. We call it lamina. We call it plural lamina. So I want you to imagine a really, really thin plate. Okay, so virtually having no height to it. Okay, really thin plate lying on the XY plane. Now I don't need it to be perfectly square. I can be any shape that I want. Okay, whatever, it's just some sort of region, if you will. But it has a mass to it. And I want you to think, so this little plate, flat, thin plate, doesn't have to be rectangle, but a thin plate lying somewhere on the XY plane. That's called a lamina. Think like laminated, like layers, okay? So the first little teeny layer. If that lamina has a mass density function to it, so what mass density function says is that the mass doesn't have to be homogeneous. It doesn't have to have the same exact distribution of mass everywhere. It could be really heavy on one side and really light on the other side. That doesn't matter, as long as we have a function telling us what happens with the mass at any point, the mass density. So it says, hey, if a lamina has a mass density function, so it tells us the mass density at any point along that plate. Do you guys get the idea? Not necessarily homogeneous. Could have different mass densities along that plate. Then the mass of the plate is given to us by a double integral over the region that plate occupies. Rectangular or not, I don't care. Of the mass density function rho dA. Let's go, wait a minute. Isn't that just a volume of that function over that region? Yes. But just like we can use volume to represent area, this has two connotations to it. Yeah, that is a volume if that's a surface, but if that's a mass density function, this will give us the mass of the plate that's occupying that region. That's what this does for us. So we have these two ideas for double integrals. Yes, they talk about volume, but they can also represent the mass of a really thin plate on a region. This is really analogous to a Calc 1 idea. Think back to Calc 1. A single integral represented area under a curve, or it represented the mass of a straight wire given a mass density function. There was two ideas. A 2D idea, area, and a 1D idea, mass of a straight line. This is now the same thing. We have a 3D idea. It could be volume, or a 2D idea, the mass of a really thin plate. Really thin means really thin, okay? Like having no height. The mass of a really thin plate. That's how we can think of these double integrals for this application. So what we're going to talk about is, with this idea, can we find out a couple things about this? Firstly, we're going to talk about moments of mass. So first, moments of mass. What this is, what the first moment of mass is the tendency for a lamina to rotate about an axis. And we're talking about the x-axis or the y-axis because this plate's on the x or the y. So the tendency for this to rotate about an axis. Can you picture the plate? I drew a rectangle here just because it's easy, but it doesn't have to be a rectangle. Can you see the plate, the lamina that I just created? Here's what a first moment of mass means. It says, hey, what's the tendency for this plate to want to revolve around the x-axis? What's the tendency for this plate to want to revolve around the y-axis? So if I just hung this out here and let it go, does it want to rotate a lot? Does it want to rotate a little? Well, that depends on where it is. It also depends on what the mass density of that plate is. Imagine this. What if all the mass, now I hope that you are listening right now, what if all the mass is concentrated, and let's say around the x for right now, okay? Let's say all the mass is concentrated right there. Is it going to want to rotate? Yeah. Let's say all the mass is concentrated right there. Is it going to want to rotate? Yeah, but less. That's the tendency. Does that make sense? So the further away, listen carefully, the further away from the axis of rotation, the more likely this is to want to rotate, where the mass density is, the most mass density. But here's the thing, please look carefully. If I'm measuring the mass density away from the x-axis, can you see that that's measuring along the y? Along the axis that's perpendicular. So I'm saying, hey, I want you to rotate about the x. And I'm measuring mass density away from the x. It's going to be y measurements. Do you see it? Cool. I'm saying, I want you to measure the tendency to rotate around the y-axis. It's going to be measuring mass density away from the y, along the axis that's perpendicular to it. Spit all over. Sorry. Along the x-axis. That's cool. So we're going to talk about that. The first moment of mass with respect to x, around the x-axis, and the first moment of mass with respect to y, around about the y-axis. So what this means, m sub x, this would be the tendency to rotate about the x-axis. I gotta be honest with you. The notation here gets kind of crazy because we're going to be talking around the x-axis but using y values. We talked about y. It's around the x-axis. The mass density is measured away from it along the y and vice versa. So the notation gets a little tricky. You make sure your notes are correct on this, okay? I don't want you getting this all screwy on your notes. This right here is the tendency for the lamina to rotate about the x-axis. Here's how we find it. No proofs, just statements, no proofs. Here's how we find it. We're going to find a double integral over the region that the plate occupies. Now, I hope that you see this. Naturally, we're going to need the mass density function somewhere in there because we want to figure out how this mass is distributed about this plate. Does that make sense? We're going to need that. So yeah, we get the mass density function. It is a double integral, so we get the dA, either dx, dy, or dy, dx, or polar even. Oh, hey, there's a thought. But we're going to get something else. Notice. This right here, this is just the mass of the plate. You guys see it? Same thing. To get the first moment of mass, the tendency to rotate about the y-axis, we're going to take the distance away from the x-axis. Well, the distance away from the x-axis is a y variable. So why the y? Why the y? If I'm talking about the tendency for this plate to rotate about the x-axis, I'm taking the mass density, but I have this idea that the further the mass density is away from the x-axis, the more likely it is to rotate. That's a y value. As I move perpendicular to the axis of rotation, I move along the axis perpendicular to the axis of rotation. If I'm trying to rotate around the x, the measurement for the mass density is a y value. Do you guys see it? The perpendicular nature of that? Think about a wrench, if you will. If you're trying to turn this thing around the x-axis. You have this wrench, right? The further out along the wrench you are, the easier it is to turn. But that wrench is measured in the y-axis. Do you guys get it? If I hold the wrench really tight to it, it's not going to want to turn very much. Well, the way away from it, it's a lever arm. It's going to really turn. So that way away, that's a y measurement. Though really close, that's a y measurement. That's where that comes from. Show of hands feel okay with that. It's good that you understand it. So likewise, if I'm trying to, maybe you can figure it out. What's this going to represent? The tendency to rotate about the, okay. It's still going to be a double integral. The plate still occupies the same region. I still have a mass density function. But for the same reason as this. If I want to find the tendency to rotate about the y-axis, I want to find out mass density as it relates to the perpendicular axis. Further out, more tendency to rotate. Closer in, less tendency to rotate. That's an x measurement. That's why we get a little x right there. Is it clear enough for you right now? I'm going to leave you with one final concept. It's called the center of mass. What's pretty cool about this? This gives us a way to calculate the center of mass for any really thin region that has a mass density function. Here's the idea. If I take and average the mass density along the x and average the mass density along the y, averages always give centers. Anybody taking statistics? You know, if you average something, you find the center of something. So if I take the mass densities here and I average them, oh wait, that kind of gives us some stuff related to from the x-axis and from the y-axis. If I take those mass densities and average them, so take all of the mass density function and divide by the mass, it's going to give me an average. Take all the mass density function, divide by the mass, it's going to give me an average. If I do that, I can find out the x-coordinate and the y-coordinate for the center of mass. I'm going to show that to you. Center of mass for any lamina. Here's how you find it. The x-coordinate for the center of mass looks a little funny. If you've never taken stats, that looks really funny. You go, x-bar, what is x? X-bar represents an average. That's what it is in statistics, and that's sort of what it means here. What this says is, if I want to find the x-coordinate of the center of mass, I'm going to basically average the mass density function as it relates to distances away from the x-axis. Please listen carefully. The distances away from the x-axis are all going to be y values. Do you see it? They're all measured in y values. So if I want to find the average away from the x-coordinate of that, it's going to be y values. It's going to be the thing that we just found, the tendency to rotate about the y-axis, divided by, the mass. I said y values in that y-axis. Sorry about that. I want to think through it with you one more time. If I want to find out, I think I had that backwards in my head. If I want to find the center of mass along the x-axis, like this, like that, I'm basically taking the likelihood, the center of mass, out from the y-axis and divide it by the mass. So the tendency about the y-axis, yeah, because those are actually my x values. You see the x right there. So m sub y, that's the tendency to rotate about the y-axis. Notice how those are x values. You guys see it? I just said the verbiage a little bit backwards, my apologies. So if I'm rotating about the y, it's all measured along the x. I say, hey, let's take that and let's average it. Let's take all of this mass density function. Let's find the tendency to rotate about the y. Divide by the whole mass. It's giving us an x value. You can see x right there. Divide it by the mass, and we get this. If we do the y coordinate, I'm running out of time. It's backwards from that. It says, hey, what if I wanted to find basically the average of the mass density along the y-axis? Look. If I want to find the average along the y-axis, I'm going to take all the tendency to rotate about the x. That's a y measurement. And I'm going to divide that by the mass. So if I take this, which is y measurement along the y to rotate about the x-axis, and divide by the mass, that would give me the y-coordinate of the center of mass. If I want to find the center of mass itself, hey, it's just a point. Take the x-coordinate, take the y-coordinate, we find the center of mass. I did kind of have backwards in my head a little bit that explanation. Did that make sense to you about how we're kind of switching variables until the notation gets funky? So when we're going the x-coordinate's got to be here. Got to be measured along the x-axis. This is the thing that measures along the x-axis. It's a rotation about the y, but about the y measures along the x. So we use that for the x-coordinate. If I say, okay, what about this one? That's a y-coordinate. It's got to be measured along the y. Well, rotation around the x measures along the y. So we take this one divided by the mass to find the averages along the y. That's the basic idea. Yay! We're all brainwashed now. Excellent. So let's continue with the brainwashing, the torture of mathematics. It's so fun. We talked about in section 14.4 just last time what these things called first moments of mass are, what the center of mass is. What people normally use the first moments of mass to do is find the center of mass. That's typically how it's used. Now we'll talk about moments of inertia, that's second moments. So first moments have to do with mass, second moments have to do with inertia, and how that relates. I want to recap just a little bit so your minds are fresh, so I don't just blow right through a problem and be like, what did we do? So here's the recap. A lamina, a super thin plate that's occupying a region on the XY plane. I've drawn a rectangle. It doesn't have to be a rectangle, but we kind of talked about this. What's the thickness of that plate? Negligible. Infinitesimally small. It's super thin, okay? Does it have a mass? Yes. Do we do a Calc 3 idea with this better? A triple integral idea with this better? Yeah, we do. But right now, we can use it for some different concepts, and we'll talk about that. If the function we're dealing with is a mass density function, that's just familiar. If that's a mass density function, then a double integral will give the mass of that really thin plate. Flat, really thin plate on a surface, on a plane. Show of hands feel okay with that. Whatever the region is, if the mass density function is there, a double integral gives a mass of that. That's the idea. Now, we had some other ideas. That plate, if I just let it go, it's going to have a tendency to rotate, perhaps, around the x-axis and or the y-axis. We can measure that, but keep this in mind. If I want to measure the tendency of this plate to rotate about the x-axis, where the mass is distributed in the axis perpendicular to the axis of rotation matters. If the mass is more heavily distributed out here versus out here, it's going to rotate differently or have a different tendency to rotate about this x-axis. Does that make sense? Where the weight is placed this way has no effect on this x-axis. Do you guys see the difference in that? The rotation about the x-axis has to do with where the mass is distributed along the y-axis. Does that make sense? So the tendency to rotate the first moment of mass around the x-axis is really according to a y value, how far that mass is spread around across the y-axis, perpendicular to that x-axis. Should you feel okay with that idea? It's a weird idea. Likewise, imagine this. If I'm trying to measure how likely it is for this plane to rotate about the y-axis, it really depends on where the mass is distributed on the axis perpendicular to it, along the x. The further out it's distributed along the x-axis, or the further in it's distributed along the x-axis, affects its rotation around the y-axis. Does that make sense? Where the mass is along here has no effect this way, but where the mass is along the x-axis has every effect on its rotation around the y. So it's a little weird, But the axis of rotation, we take the perpendicular axis to measure its tendency to rotate. That's the idea. So around the y-axis has everything to do with where the mass density is placed along the x. Around the y, how it's distributed along the x. Around the x, how it's distributed along the y. It's almost like it's just reversed. I don't know if you're okay with the idea. Then we said, well, now what would the center of mass be? The center of mass would basically be center. Center means middle. Middle means an average. If we take how the mass is distributed, so its tendency to rotate about the y, please follow, I don't want to lose you. Its tendency to rotate about the y is an x value measurement. Do you get it? So if I want to find out the center of that, I'm going to take the x value measurement, where that's at, and average it by dividing by mass. So the rotation about the y, that's the rotation that has the x value in it. Rotation about the y has the x value in it. I'm going to take that, divide by mass, and it's saying, hey, take that distribution around the y, has to do with x distribution along the x-axis. Take that distribution and average it. It will find the center of that mass according to its x-axis. So the variables get all screwy here, but you see that this is really an x measurement. I don't know if you do see that. Likewise, this one says, well, okay, well, what of the average of the y's? Well, let's look at the rotation around the x. If I talk about the rotation around the x, that had to do with where the mass is along the y. So let's take that measurement of rotation around the x, which is the y value, and average it, divided by the mass. Then it's going to give me some measurement along the y-axis. That is the center of mass. When I take the x-coordinate and the y-coordinate, I get center of mass for that lamina. That's pretty darn cool. Should eventually be okay with that one. Now we're going to step it up to the next level, the second moments. And we call those inertia. Inertia is basically, you can think of it, how hard it is to get something moving. Once you get it moving, how hard it is to get it to stop. Inertia is this idea of, you know Newton's laws of motion, right? The whole object at rest stays at rest, object in motion. That has to do with inertia. So we can measure that also, second moment of inertia, about the x, about the y, and about the origin. So about the x, think about this. How hard this would be to get moving, how much we'd have to affect it to get it moving about the x-axis. Again, if it's about the x-axis rotating this way, the measurements would all be y measurements. Does that make sense? We talked about how the mass is distributed along the perpendicular axis, then that would affect its hardness to move around the x-axis. Always the axis perpendicular to it. Is that clear for you? So here we go, okay, well, if I'm talking about moment about the x, it doesn't matter how it's spread out this way, it matters how it's spread out along the perpendicular. Why? However, for moments, that's the same as that, so it can't be exactly the same, but if we square it, that right there, that y squared, and then the mass density function will give you a measurement of how hard it is to get that lamina moving around the x-axis. That's what that's telling you. The larger the number, the harder it is to get that to start moving. And now if you feel okay with what I said. What's this going to be? For the same reason as before. Want to move around the y? Well, it doesn't matter how the mass is distributed along the y, it matters how the mass is distributed along the x. So it's an x measurement, and we take x squared. Yeah.
Would that value that you get from those have a unit to it, or is it just a value?
That's a good question. It probably has to do with the way that the mass is unitized also.
Okay.
So I don't know whether we're in pounds or kilograms or whatever, but it's going to have some. Yes, it's going to have a certain measurement depending on what units we're doing. I'm going to keep it unitless. We're going to keep it as easy as we can, sadly. But when you get into your more engineering and physics classes, you're going to have this sort of stuff. Now, the origin. Origin's real easy. If you can find this and find this, the origin adds them. The last concept we have is this thing called the radius of gyration. I want you to imagine it this way. Imagine that on this plate, all the mass is localized at a single point. Can you imagine that? It's all localized at one point. That one point would be the best point to push it to get it to move where you want it to go. Does that make sense to you? So basically that. kind of be the center of mass, right? If you push the center of mass, it has a likelihood to move the whole figure and not start rotating it, not gyrate it. So that's that. Think about the center point, or think about where the mass is localized, centralized. If all the mass is at one spot, that would be the best point to push this plate from. Does that make sense to you? Well, where that is, according to the x-axis and the y-axis, is called the radius of gyration. Radius of gyration about the x, and radius of gyration about the y. Best place to push it from to get it to go around the x, or best place to push it from to get it to go around the y. Does that make sense to you? That's what these things refer to. So the radius of gyration around the y-axis, think about this. If I'm going around the y-axis, that is going to be an x measurement. It's going to give me someplace over here to push it. So I'm going to have, it's not x bar, it's not just the center mass. The radius of gyration goes a bit further, deals with inertia. So here we take our second moment of inertia about the y, matches up, divided by mass, and for about the x-axis, it's a y measurement. Takes the second moment of inertia, about the x, and divides by mass. Those are formulas. Just want you to see that the variables, even though they're wacky, they do match up. If I'm talking about the x-axis, moment of inertia, or the radius of gyration about the x-axis, well, that's a y type of measurement. That's why we have that about the x, a y type of measurement. Well, wait a minute, that's an x. Well, look closely. That x has your y's in it. Does that make sense? That's where that's coming from. That's why the variables get totally like, heck. But just think that our movements here are perpendicular to the axis of rotation that we have, and then you're typically okay with it. Are you guys understand where the formulas, at least where they basic, I'm not proving any of it, okay? We don't have time for that. But do you understand where they're at least coming from, the ideas of these things? Yeah or no? I'd like to do an example to show you how they work. I gotta be honest with you. I'm gonna give you a really, really easy example. The other ones are much harder. They take a lot of time. Things get crazy here. Because you got a lot of stuff being multiplied and integrated, and your regions don't have to be nice. They can get pretty darn crazy. I'm gonna give you a rectangular plate. I'm gonna give you the idea of, and you find a lot of stuff. You're finding all of this stuff. So we're gonna find all this stuff with a simple example. So here we go. And I'm going to do it over here so I don't have to erase all that. Let's find the center of mass and the radii of gyration, plural, we want to find both, for a lamina with a mass density of that, and occupying a region given by the following coordinates. Hey, do y'all recognize these are all going to practically be double integrals? Did y'all see that? Yeah. So what's the first thing you always do with any double?
Draw the region.
Can you please draw that region? Draw the lamina. The lamina is the region, and vice versa. That right there is the thing that I want to try to find all this stuff about. The center of mass of that lamina, and the radii of gyration of that lamina. Now, you're like, man, you're only asking me for two things. Well, I'm not. I'm a tricky teacher. I trick you. What do you have to know in order to find the center of mass? Well, for this, you need that. And for that, you need that. For both of them, you need that. For each one, you need these. So that's 1, 2, 3 integrals, double integrals. After that, you go, well, this is pretty easy. That's division. That's pretty easy. That's division. And then if I talk about radii of gyration, I'm going to need this, and the mass again, and divide them into square root. So we're going to do that, and it's not going to be hard because this example is an easy one. But can you imagine if the mass density function was kind of screwy, or if the region was kind of messed up? That would get intense. Because you'd have to do 1, 2, 3, 4, 5, a minimum of 5 double integrals that can all get screwed up. Make sense? That's tough. I'm trying to tell you that I'm going through the motions here, but these can be very hard problems. So let's start with the basic one. What's the first thing you might want to do?
Yeah.
Give up. It's not that bad. Start here.
Yeah.
Run down this list, create this. Run down this list, create the radii of gyration. So start with the mass. Set up the double integral for the mass. I'll tell you what, though, this would be good practice for you for setting up integrals and practicing them at least. I hope you remember how to set up double integrals. We set these up with the mass density function on the inside. Everybody right now, what's the mass density function for the inside?
1.
So we're going to leave that there in just a second. It's given to you right there. What I do set up first is a double integral. Now, look, that's your region, right? So what type of region is that? It's a nice thing. I can go either dx or dy. What theorem says that you can go either one and be fine? So for Fubini's theorem, you go along the x first or along the y. It doesn't matter. I will tell you, I'm going to go along the x first. Here's why. Because my mass density function has a y in it, I want to integrate with respect to x so I don't have a fraction. I don't want to do 1/2 y squared and plug into that. Does that make sense? No?
Yeah.
If not, integrate however you want. It's going to work out the same. So I'm going to go, you know what? I want to do dx first and then dy. Let's get it right. Let's do it together. If I go dx first, am I going up or across? From what function of x to what function of x? Remember, these are actually functions. What function of x to what function of x? Perfect. And then what constant of y to what constant of y? 0 to 2. You guys are going to get really good at this really fast. So I have my setup along the x 0 to 3, along the y 0 to 2. I put my mass density function right here, and that will give me the mass of that lamina occupying that plate given that mass density function. Whew, that's a lot to say. Did you follow that? Now, can we do it? Let's work on it. Let's go quickly. If I evaluate with respect to x, I'm going to go from x equals 0 to x equals 3. We're going to plug that in, then we're going to integrate with respect to y. So this is mass equals 0 to 2. That looks like we get 3x minus 0. Or sorry, 3y minus 0 dy. Well, y'all know how to do that. That's 3y squared over 2. From 0 to 2, that's, how much is that?
12 divided by 2 is
6. Fairly painless. That's the mass of that mass, whatever units we have, that's the mass of that lamina. Head nod that you're okay with that one. Yes, no, yes for sure. I know we're going quick through double integrals, but is there anything here that you can't do? Thanks for playing along, guys. People are starting to ask, is there anybody sitting out there? Or are you talking to nobody? Is this guy seriously crazy? You exist, right? Okay, good. All right. Fantastic. Next thing, what would you do after that? If I'm trying to look for center of mass, what would you do? Either one of those. Can you just realize this, that as soon as you set up your region, all you're doing is adding a variable there. You've already taken care of it. It's just another double integral. So when we set this thing up, yeah, you can switch it around. I almost never do. This is still going to be 0 to 2. Still going to have 0 to 3. I'm still going to have a y. It's still going to be dx, dy. It's the same exact thing, only what has to go right there? Get the variable correct. What has to go right there?
Y.
About the x has another y in it. And now if you're okay with that one. Okay. Zero to 2 for the y's. We integrate with respect to x. We leave that y squared alone, integrate with respect to x. We let x go from 0 to 3. We don't forget that we're going to have a dy after that. We got 0 to 2. If we plug in 3 and plug in 0, we're going to get basically the same exact thing. It's just going to be 3y squared that we integrate. dy. Well, that's going to be y to the third from 0 to 2. How much is that going to give us?
2.
Oh, we're practically done. What's the next thing you do?
Same thing.
Can you do that? Go for it. Try it. At least try the setup. It's going to be practically the same setup. I'm going to have to start moving over here because I'm running out of room, but I'm just continuing this problem right up there. If I'm going to do the first moment of mass about the y-axis, I need an x right next to my mass density function. I got to have another x. How many people set that up correctly? You got that? That makes our integration a little bit tougher because now we actually have a variable that we got to integrate with respect to x. Not horrible, but we do have to take that into account. So there we'll get that 1/2 x squared from 0 to 3. Did you guys make it that far at least? Perfect. Oh man. Looks like we get what from that? 9/2? Sure. 9 minus 0 is 9. Halves, 9/2 y dy. And if we integrate that, we're going to get what?
9/4 y squared.
9/4
Y squared
from 0 to 2.
What's that become?
9.
Beautiful. Not so bad. Now, let's see what we needed. We needed m sub y over m sub x over m. We have those things. So what I want you to do right now on your own, can you please find the x coordinate for the center of mass and the y coordinate for the center of mass? It should just be dividing numbers. X, I take this one over mass. Y coordinate, I take this one over mass. Got that taken care of. Center of mass is always a point on your lamina. Tell me what the center of mass is, or what point the center of mass is at.
9, 6, 8, 6.
Do we know how to simplify?
Yeah.
3/6. You shame me. What is it?
3/2, 4/3.
You give me this on your test, you shall not pass. No, too much? Little dramatic? It's Gandalf, dude. Gandalf will not pass you on that. For real. Simplify your freaking fractions, alright? Come on. That's center mass. Hey, we are now halfway done. Let's go ahead, let's find the rest of it. For radii of gyration, here's what I want. We're going to do the integrals super fast. What I want is the setup for this, but recognize it's the same region. You're going to have the same numbers. You're just plugging in different functions in front of your mass density function. Does that make sense to you? I'm going to erase this stuff, and we're going to do the work over here, okay? But I want your setup right now. I'm going to give you about 30 seconds. Set up both of these things, and then we'll do them together if you have to, but at least set them up. They should look practically identical. Practically identical. The only difference is the thing that you're multiplying in front of your mass density function. So for this one, the about the x, it should be y's. About the y, it should be x's. And we just square them for second. That should make some sense. First moment's power 1, second moment's power 2. That's a nice way to remember that. That's kind of always the opposite. Oops. Always the opposite axis. So second moment of inertia about the x-axis, we have that y squared there. This should be what? And then we do just some basic integration. I'm going to do it real fast. I'm going to do it correctly real fast. That's why I write it. That's why I write x. And x, I'll forget it. Basic integration. I know you can all do it. Get 12. You guys are okay with 12. Next one, a little bit different. Let's see now what that's gonna be. That's 27 minus 3. 27 times 1/3 should be 9. Hopefully 18. Did y'all get 18? We're close to done. If you needed second moment of inertia about the origin, you add those two together. If you need to find the radii of gyration, I erased the formulas, but the radius of gyration, for about the y-axis, that's what this is giving us, for about the y-axis is an x measurement, and what we get out of it, we take the second moment of inertia divided by mass. Second moment of inertia about the y, that's the x measurement. I believe that formula I gave to you earlier, yeah? So we're going to have the square root of, let's look back to that number. How much is that number? Divided by the mass we found at the very beginning. What's that?
6.
Square root of 3. So that's the radius about the y-axis. It's an x measurement. So away from the y-axis along the x measurement, that's where that, how far away you push that to get it moved best around the y-axis. That's what that's saying. The next one, this guy, very similar. Just take the other number you found. So we're going to have our, 12. That's the radius for about the x-axis. Head nod if you're okay with that one. We have one more thing to talk about. It's very brief, and then we're going to call it good. Trust me, it's very brief. I just want to show you a setup on one more because I have to. Because I have to. I need to show you this one. The problem with this is the region. This right here is the lamina that we have, that triangular little plate. That's the lamina. So if we wanted to set up for the mass and the first moments of mass, this is all we're going to do. The problem is you're going to have to define that region appropriately. Let's see if you're ever paying attention to anything we do with regions, you know which direction you should go across first. This way? This way? This way?
Yes.
Why? What's the difference? Why? Why wouldn't we go dy first? If I do, well, this is y equals 0, correct? That's y equals 0. This right here, you'd have to find the equation of those lines. So you have a choice to make. You can do this for that, or you can do this. But the problem is, if I'm going between two functions, right here I have to switch. Right there I have another integral that you're going to have to do 5 times. A double integral 5 times. Do you want to do that? Yes. No. Do you see the difference in the change in the functions? We've talked about it a lot, but to go between here and here, you're not always going between the same two functions. Here's between 0 and this, 0 and this, 0 and this, 0 and that. As soon as you go 0 and that, you switch over. That's a bad thing. You don't want to do that. Go the other way. If we go the other way, yeah, we'll have to solve this for the functions with respect to x. So x equals 2y, not this. And x equals, well, I wrote it down. I want to do my name. I messed it up. That, I believe?
Yeah.
My head's fuzzy, man. Can you please follow that and see if that's right?
Yeah.
I need to double check on my math.
Yeah.
Doing Calc 3 for 3 hours hard. Times 2, times 2, 3. Okay. Yes. Okay. this is the way we want to go first. This is the way we want to go second. So if we're going to set up the mass for this thing, the mass would be a double integral. What would we do first, dx or dy? And then dy, so this has to be x equals stuff, and this has to be y equals constants. Let's do the x equals first. What's the small function when I'm going from left to right? What is it?
2y.
And everybody, come on, big function, what is it? And the y's, where do the y values go from?
0.
Perfect. What goes in here for the mass? That's the typical way that we find mass of any lamina, of that region. That's it. If I wanted to find this, what would I be putting in there?
Y.
Same stuff, same region. And if I wanted to find y, I'd be putting in same stuff, same region. That's the idea. That's the setup. But this stuff is going to absolutely kill you with distribution. Can you see it? You're going to be distributing like crazy on that thing. And then you got to do second moments, and it gets a little bit nicer than that. But that's at least a setup. Can you follow the setup on that? The big thing here was, do you understand why we're doing dx and not dy? Is it making sense? Mm-hmm. Cool. So I want to give to you some examples that illustrate what we can do with this 14.4 material. This stuff like, well, you know, what is a density function? What does it do? Does it just have to be a mass density function to find stuff? And the answer is no. No. If we have a mass density function of a region and we integrate across that region, we do get the mass. But if we have a different type of density function, we can get different things. So for instance, let's consider this, we have a plate. We have this plate that's been electrified, all right? And the plate that's being electrified is given by this. So we might have a picture of what that looks like already. We're going to draw the picture in just a second. Anyway, but I know that the charge is not evenly distributed. The charge is distributed with a charge density of that thing. So let's go ahead and let's find total charge of this plate. How much charge is on this plate? Now, when we talked about mass, mass was a double integral over the region of mass density. So charge, total charge, can be thought of the same way. For total charge, we could do, let's call it Q. Total charge is going to be a double integral over the region that the charge is spread across of whatever the charge density function is, integrated across the region that it's spread with respect to the area, about the area of that region. Head down if you're okay with that one. Does it look familiar? It looks like mass density, except now we have charge density, so it's going to give us total charge rather than total mass of that region. Well, what's the first thing we always do when setting up a double integral? What do you do? Let's draw the region. Is this the region? No, that's just the charge density. The region is given to us by, hey, it's spread across that. Let's draw that. So what plane is it on?
X, Y, X, Z.
XY plane. Can you draw? What does it look like?
Circle.
Kind of looks like a circle. Oh, but wait a second. It says that we got ourselves a circle with a radius of 2 for sure. But it also says that our y has to be greater than 0. So this is full circle. It's a disk. That would be a disk. This says it's the top of that disk. So the region is really this one. And now if you're okay with that one. Now, let's go through the process. What type of region is it? Circular or rectangular? Would you want to use rectangular coordinates or polar coordinates?
Polar.
Circles, polar. Man, so much easier. Don't try defining this stuff in terms of, oh, y equals the square root of 4 minus x squared. That's crazy, man. Don't plug that in. You're going to have trig subs to do. I don't want to do that. I want to make it easy. Let's redefine this in terms of polar. So if this gave us x squared plus y squared equals 4, then I can redefine that in terms of polar. What's it going to be redefined as? Yeah, sure. r equals 2. That's so much nicer. So we want to go across this region. Well, we're going to start changing this. So with my total charge here, I'm still going to have a region. We're going to start defining this region right now. But I don't want dA, everyone in class right now, you tell me what that's going to change to for polar. Beautiful. Which means I'm going to have r equals here. I'm going to have theta equals here. Please help me out with this region. When we start this, we always go across r first. We start at the origin, we immediately intersect our region, and we end up hitting some polar equation, r equals 2. So what's it set up as?
0, 0 to 2.
If you like the method of going, hey, let's mash r between two functions, that's nice. That shows you exactly what you're doing between 0 and 2. Head nod if you're okay with that one. Now the theta. Whoa. 0 to 2 pi.
Sure.
If you want to get it completely wrong. Why? Why? What's going on? It's only half. So for our theta, I know I'm not going from, I didn't start at 0, but I'm doing this. I'm not making it all the way around. I'm stopping at pi. Show of hands if you're okay with that one. That's our setup. We got r dr d theta, no problem. R equals 0 to r equals 2, then r theta equals 0 to pi. Now, what goes here? That piece. Only you need to look carefully at it. There are none of these variables over here. There's no x's, there's no y's. This is something that you need to change before you start integrating. If you don't, you can integrate with respect to r, but you're gonna mess this piece up because this has r's in it. Does that make sense? So when you don't have x's and y's over here in your dr d theta, you need to change this immediately. That's important. You have to do that. So let's try to do that. What's that going to become?
R.
So we should have r times r dr d theta. We've already done our setup. The setup's the most important part. I'd like you to try to do that on your own here real quick. Not going to give you long. It shouldn't take you long, honestly. Integrate respect to r, no problem. Plug in some numbers. Respect to theta, we get 8 pi over 3. Did you get 8 pi over 3?
Yes.
Coulombs, I believe, if my verbiage is correct. That's the charge. That's the total charge of that plate. That's the idea. And now if you're okay with it. Easy, medium, hard, what do you think? Compared to some of the stuff we've done, this is a pretty piece of cake. Let's try to set this one up. Then I'm going to give you one on your own to do, okay? So this guy, average temperature. So here's how average temperature works. It takes the total temperature and divides it by the area. That says, hey, how much total temperature I have spread across evenly the area. That's where that comes from. So we have 2 tasks to do. Number 1 task, we need to find the total temp. So the temperature at any point on a hot plate with this dimension is given by this function. That's a nasty guy, but that's the function that gives the temperature at any point on this particular hot plate. Here's my question. If I asked you right now what the region looks like, would you be able to tell me? The dimensions of the hot plate is the region. So what's the region look like? Radius? It's like this disc, right? This in the hot plate looks like a circle. That's our hot plate. That's going to give us our region. Does that make sense to you? This right here, if our temperature, the exact temperature is given to us by this, ladies and gentlemen, that's a temperature density function is what that is. It's telling us the temperature at every single point on there. This is our density function. It just has to do with temperature at this point. So let's go ahead, every single time we do a double integral, we draw the region. Let's draw the region. In our case, our region is simply a circle on the xy plane. with a radius of 4? Is it the whole circle?
Yes.
Well, let's see. Is there anything that's restricting that disk? If you're seeing something, then tell me what it is. Here, the only restriction was that y had to be greater than 0. Do we have any of that here?
No.
So our hot plate, we're talking about the entire hot plate. That is our region. Show of hands if you're okay with that one. Also, this is given to us by x squared plus y squared equals 16. That's how we ended up getting that. What type of a region do we have? That's exciting! No, not so much. I'm excited because I love using what type of system. Just makes things so nice with circles. So let's redefine it. If x squared plus y squared equals 16, then r equals 4. That's nice. That's really, really nice. Let's start finding the total temperature here. So if we know that this is my region, and I want to define this region in terms of polar coordinates, I first understand that my total temp is going to be a double integral across the temperature density function, but I am using a polar region, so I'm going to have an r dr d theta. Head nod if you're okay with r dr d theta. I know that my r is going to go from, okay, you help me out. What two numbers, please? 0 to 4. Yeah, we actually had r squared equals 16 and then took a square root. So from 0 to 4 first, and then we have the whole circle here, so we're going to do theta equals 0 to theta equals 2 pi. So far, so good. Yes, no? This matches r's with r's, thetas with thetas. I have my r in front of my dr. I know I have to have it for polar. Ooh, the temperature density function has to go here. This whole nasty business has to go here, but there's a problem with it. What's the problem up there? X and Y's. I don't have any X and Y's. It'd be impossible for me to integrate this. And this has an R built into it. So if I take my 400 cosine nasty stuff, I start changing it, what's that going to give me?
0.1R.
Just R. 0.1 R. This is square root of R squared, so we just get R. I want to pause for a second here. I want to talk about something else. Number one thing I want to talk about is, do you understand the setup? How to get the region? How to see what this is? To set up your double integral and understand that this right here is going to give you total temperature. This is temperature at every single point in degrees Fahrenheit. This adds up all the temp. That's our idea of total temperature. It's kind of a weird idea. But then from here, we're going to spread this across the area. Let's talk about the area. There's two ways to do it. One's a really intuitive way. What's the area of a hot plate with a radius of 4? 16 pi? Because you get pi r squared. It's a circle. Love polar. It's circle. So this would be 16 pi. The area would be 16 pi. Does that make sense to you? If you didn't do that, you're like, whoa, well, wait a minute. I don't understand the area of a circle. Well, yes, you do. But you could do this. If you had an awkward region, you could define the region like that. You could find the area of any region. So if I had an oddly shaped region, hey, do a double integral over that region with a 1 right there, dA. And you could go, well, then this is going to be r equals 0. It's going to look, guys, it's going to look identical to this, except you ain't going to have this. It's just going to be 0 to 2 pi r dr d theta. And if you work this out, you're going to get your 1/2 r squared. You're going to get that 8. Do you guys see the 8 that would come out of that? And then the 0, okay. Then you integrate and get a theta, and you plug in the 2 pi. You're going to get 8 times 2 pi, 16 pi. Same exact story. What's going to happen? I'm not going to do it for you. I'm not going to do basic integration for you. Right here, right here, this is the most challenging integral that we've come across so far. Because if you look at this integral, there's only one way that we know how to do that. Do you know how to do that?
Integration by parts.
That's by parts. Because you have a variable and then cosine of that variable with a constant. This is kind of a nasty one. It gets pretty crazy. This is by parts, then you plug the numbers in, then it's very easy, okay? But this is for sure by parts. Do you want the answer to it?
Yeah.
Are you going to try it on your own? Do it. Try it on your own, for real. It's good for you to do that. It's good for you to not have me go through all this stuff and spoon feed you. You need to eventually be doing this stuff on your own and getting it right. This is by parts. Your U would be the R. The V would be integral of the rest of the stuff. You do know how to do integration by parts. UV minus integral of V du. Another integral to do. You plug in 0 to 4. You work it all out. Then you integrate with respect to theta. You just plug in 2 pi and 0. That's the easy part. That's really easy. What this ends up giving you, this really awkward number around 19,000, 19,309.066. What that is the temperature added up at every single little point there across that surface. That's what that is. Does that make sense? If I want to find average temperature, then I take my total temp and I divide it by 16 times pi. If you get that, the average temperature would be about 384.1 degrees Fahrenheit. With me? Yes? No? As I'm erasing the board on this side, I want you to try one. This is actually quite useful. If you didn't know this, a lot of times population density can be modeled for a city. So they have these formulas that say roughly about this many people live within half a mile of the center of the city. Roughly how many people live within a mile, 2 miles, whatever. And if we have that population density, we can find the total population around the center of a city. Is it useful to know the population of a city? Yeah, pretty useful for a lot of reasons. So we're going to try that, given that someone actually has done this for their city. And hopefully it won't be a surprise that this is going to be based on the natural number E. A lot of times population growth, population distribution is based on these really not random, numbers that come up, like E, stuff like that. So let's find this one. So here's the population density for a city. And what I want to do is I want to find the total population within a mile of the center of the city. I believe I gave this to you as a homework problem too, so it should look familiar. Or unless you haven't done it yet. Probably haven't. So given a population density function, I'm asking to find the total population within 1 mile. This is exactly like finding mass, exactly finding total charge, exactly finding total temperature. You're given a population density function. You got a density function. You got a region that we're going to have to define. And if we take a double integral over that region of that density function, it adds up the population. That's what's happening here. That's kind of cool. So let's first do what we always do with double integrals, which is what? Let's draw the region. Now, wait a minute. If that doesn't give us a region, this thing has to. What's population within a mile of the center?
Circle.
With a radius of... That's what within a mile means. Well, let's cut right to it. If we know the radius is 1, I'm not messing around with x squared or y squared or anything. I know this is a circle with a constant radius. The radius is 1. I know it's a full circle. It's going 0 to 2 pi. So our r is matched between 0 and 1. Our theta is matched between 0 and 2 pi. That right there, that's basically our setup. All we have to do, change a couple things about this, and do a double integral. So double integral, since we're over a circular region, I know I'm going to have a polar coordinate system for my double integral, r d theta. I know that my r comes first, my theta comes second. I know that for r I'm going from 0 to 1, and theta is 0 to 2 pi. I also know that these have no x's and y's. So if I have any x's and y's in this population density function, I'm going to have to change it. And I'm giving you kind of a nice one. The nice one here is that 3,000 stays, the e stays, the negative stays, but that changes to what? Y'all should know what to do next. What do you do next? Nope, easier. U sub. Can you do a U sub? Change the bounds, tell me what you get. Did you make it that far? Did you make it to the setup and at least the first little iteration of this thing? Do you see the issue that we have with our bounds?
Yes.
Did you get that negative?
Yes.
If we switch the bounds, what happens to the negative? Okay, we're going to do that. Switch the bounds, negative gone, 1500 e to the u, just got a whole lot, d theta. Got a whole lot easier. If we integrate that, we have e to the u where u is 0, and we have e to the u where u is -1. So what this gives is kind of something awkward. We get the 0 to 2 pi, 1500, e to the 0 gives me 1, minus e to the -1. And then I evaluate d theta. Yes?
Should the 1500 be negative if we had du over -2?
It should, because when I switch my bound, the question was, should this be negative? When I switch my bounds, it creates a negative. So a negative and that negative give me that positive. That's what's happening. Last one, hey, we just got a theta. So we're going to have all this stuff, 1500. We're going to have 1 minus e to the -1, or 1 over e, theta, and theta is going from 0 to 2 pi. So basically take all this stuff, multiply by 2 pi, So 3,000 pi times 1 minus e to the negative 1 or 1 over e. Just have a calculator, did you work it out? What'd you get?
I got like 5,957.559.
Okay, so 57 point something, and I want you to know this. If you get like 5,957 point anything, 0.3, you're, whatever it was, I think it's like 7 or whatever. But you can, hey, can you have a 0.03 of a person? Little people count, okay? My daughter counts as a person. She counts. So no. So if you have any, even if it's 0.03, this is more than 5,957 people. So you count that as a whole person. This would be around 5,958 people. That's the approximation how many people live within that center of town. So fans, does that make sense to you? That's about it. Just some examples that illustrate the concept a little bit better.